part 3 of this review. So let's jump right into number 41. Almost there. Last 20 questions. So we have another natural exponential function. So I'm going to find the derivative of this. Again, we've been doing this a couple of times now. Here's how you do it. So d dx of e to the 2 over x power is going to be e to the 2 over x times whatever the derivative of 2 over x is. Okay, now I'm going to write this 2 over x, do a little sidebar over here. I'm going to write that as 2 times x to the negative first power. So the derivative of 2 times x to the negative first power using the power rule is negative 2 times x to the negative second power. So let me write all that down now. So e to the 2 over x power times negative 2 times x to the negative second power. So now to make this look a little nicer to find my answer, I'm going to have negative 2e to 2 over x to the second power. So I'm looking for that answer here, which is going to be, looks like it's going to be D. All right. Key thing was getting that x squared in the denominator. All right, let's keep going. Number 42. Now, 42 gives us f of x and g of x, and it even gives us the graphs of lines tangent to the graph of g at x equals negative 3 and x equals 1. So it's asking if b of x is the composition of g of f of x. What is b prime of a number, which they're using negative 3 for that number. So let's first just talk about how to find the derivative of b of x. All right, the way you do this is you're going to do g prime of f of x times f prime of x. So again, this is using, let me go find it on the formula sheet. This is, I don't know if I have it on here. I thought I did. Let me check to make sure. There we go, the chain rule, right? This is the derivative. I know the letters are backwards, but just follow along with me. We have the derivative of the first, so whatever you see first, evaluated at the second function times the derivative of the second function. So that's what we did here. I saw g first, right? G came first. So I took the derivative of that, evaluated at the second function times the derivative of the second function. So now let's replace, all right, let's replace x with negative 3. So g prime of f of negative 3 times f prime of negative 3. All right, so f of negative 3, negative 1, negative 2, negative 3 is right here, positive 1. So I'm going to do g prime of 1 times f prime of negative 3. I'll write that down again. Keep going. So here we go. To find this, I need to use slopes, right? The whole idea is when you're doing this, we've done this a couple of times in part 2. All right, if I look at g of x, I'm going to positive 1, right here. So this blue line is the tangent line. So I'm looking for the slope there. It looks like it's down 1 and then right 2. So that's negative 1/2 for that slope. And I'll do the other one. So times, and this is going to be at negative 3. The tangent line is just the actual line. So let's find the slope of this line, which is up 1, right 3. So that's times 1/3. So when you multiply those together, you get negative 1/6. So our answer is B. That's number 42. 43. All right. Here it is an example of implicit differentiation, which we just got done talking about in class. So I'm going to find the derivative of 3x squared plus the derivative of, let me actually write it like this, move that constant multiple in front. So 2 times the derivative of xy, we just did a problem like that, times the derivative of y squared equals the derivative of 1. Well, the derivative of 3x squared is 6x, plus this is going to be 2 times, now this is the product rule, so the derivative of x is just 1 times the original second is y, plus the derivative of y is dy dx, times the original first, which is x, plus the derivative of y squared, which is 2y times dy dx equals 0. Distribute with that 2, so plus 2y plus 2x dy dx plus 2y dy dx equals 0. So like we talked about in class today, anything that doesn't have the dy over dx is going to move to the other side and leave the other pieces here. So 2x times dy dx plus 2y times dy dx equals negative 6x minus 2y. I'm going to factor out the dy dx. Get 2x plus 2y equals negative 6x minus 2y. And then divide both sides to get dy over dx by itself. So negative 6x minus 2y over 2x plus 2y. So this is the answer. You'll notice you don't see it, all right, because if you notice, all four terms can be divided by 2. So I get negative 3x minus y over x plus y. So I'm looking for this answer. I still don't see it, but if you factor out the negative in the numerator, you get negative times 3x plus y in the numerator, which is going to give us answer B. Okay, that was some good implicit differentiation. Let's try 44. All right, we're going to find, again, some implicit differentiation here. And then what we're going to do is plug in x equals pi over 2 and y equals 1 to find what that value is. So let's first find d dx of cosine of xy. So a little chain rule is going to happen here. And d dx of y minus 1. The derivative of cosine is negative sine of x and y times, now if you notice, inside that argument is the chain rule. I'm sorry, we're doing the chain rule right now. Inside the argument is the product rule. So I have to multiply the derivative of the first, which is 1, times the original second, plus the derivative of the second, dy dx, times the original first, and that's equal to dy dx. All right, so I'm going to clean it up a little bit. Negative sine of xy times y plus dy dx times x equals dy dx. All right, I am going to divide, let's see, I'm going to distribute, all right, first this negative sine of xy, then I'll end up solving for dy dx. So I'm going to do negative y sine of xy minus x sine of xy times dy dx equals dy dx. Move any piece that has dy dx to the left, any piece that doesn't to the right. So I have negative x sine of xy times dy dx minus dy dx equals positive y times the sine of xy. Factor it out. That gives me negative x times the sine of xy minus 1. And then finally divide out to isolate it. So y times the sine of xy all over negative x sine of xy minus 1. So that is the derivative, but we're not done yet. We have to plug in our values for x and y. Okay, so I'm going to plug in wherever I see y is a 1. So 1 times the sine of 1 times pi over 2, which is just pi over 2, all over the opposite of pi over 2 times the sine of pi over 2 minus 1. All right, if you need to go to the quadrantals, you can. All right, the sine of pi over 2, right, that ordered pair is 0, 1. So the sine of pi over 2 is 1, so 1 times 1, over the opposite of pi over 2 times, again, the sine of pi over 2. Make sure I'm going to get my parentheses right here. Yeah, all of that's together, okay. Times 1 and then minus 1. So it's going to be 1 over negative pi over 2. Oops, sorry about that. Come back. Go away. Don't know why it won't go away. There we go. Negative pi over 2 minus 1. That's a times. Okay. Now, when I look at my answer choices, don't think I see that. So let me go over here. Come on back. You'll notice I don't see that for my answer choice. Oh, where'd you go? There you are. All right, so what I need to do, it looks like they've gotten rid of the denominator. So I'm going to get a common denominator in the bottom. So 1 over negative pi over 2 minus 2 over 2, which is 1 over negative pi minus 2 over 2, which is equal to 2 over negative pi minus 2. So I feel good about that. I don't think that's going to be one of my answer choices, but let's see. I'm getting closer. And it looks like I need to factor out the negative. So if I factor out the negative, I get 2 over the negative times pi plus 2. And that negative can go on the top or bottom. So I'm looking for 2 over negative, the opposite of pi plus 2. So I have pi plus 2 and negative 2. I believe it's going to be this one. Let me confirm with what I got. I got the negative 2 over pi plus 2. Negative 2 over pi plus 2. And that's what I got. Awesome. Wow, that was some good implicit differentiation there. Good times. Let's go to 45. Another one where we have to use implicit differentiation, the value of dy over dx, and we want to evaluate it at 1, 0 again. So we have the derivative of y and the derivative of the natural log of x squared plus y squared. Now, the one on the left is a little easier, right? This is just dy dx. This is going to be a little tough here. Let me go to my formula sheet. We're using the natural log function derivative, which is right here. It says the natural log of your function is 1 over your function times the derivative of that function. So 1 over our argument, which is x squared plus y squared, times the derivative of that inside, which is going to be 2x plus 2y dy dx. Okay? Okay, so I'm going to move that to the numerator, which is 2x plus 2y dy dx over x squared plus y squared. All right. I am going to, let's see what I want to do here. Yeah, I want to move the x squared plus y squared to the other side. So I get dy dx times x squared plus y squared equals 2x plus 2y times dy dx. I'm going to distribute, let me rewrite that again. I'm going to distribute the left side to get dy dx times x squared plus dy. No, I don't think I actually want to do that. Let me pause for a second and do a little work. Okay, I'm going to go ahead and do what I was saying, which is distribute and see where it takes me. So dy dx times x squared plus dy dx times y squared equals 2x plus 2y dy dx. I'm going to get all the dy dx's to one side. So that's going to be dy dx times x squared plus dy dx times y squared. Oh, Douglas, what? Yeah, okay. That's good. And then minus 2y dy dx equals 2x. Factor out the dy dx's and divide everything over, and you get 2x over x squared plus y squared minus 2y. did skip a step there, so I apologize for missing the algebra. And then to get the answer, I need to plug in for x is, where is it? X is 1 and y is 0. So x is 1 and y is 0. So I get 2 over 1 squared is 1, 1 plus 0 squared is 0, or 0 squared is 0, 2 times 0 is 0, 1 plus 0 is 1. So you get 2. Answer is 2. Okay, that was another good one. All right, 46. It says we have all this information about f and its derivative. The function g is differentiable, and g of x equals f to the negative first power of x. So they're telling you that g of x is the inverse of the f of x function. So we want to find the derivative of the inverse. So we did this a few lessons ago. So the derivative of the inverse is 1 over f prime of g of x. So if I do this for, what's it, positive 3, it's going to be 1 over f prime of g of 3. That's 1 over f prime of g of 3, which is, what is g of 3? Oh, it doesn't tell me g of 3. Clearly I did something wrong. Hold on one second. Okay, appreciate that pause. So what I did not understand was that I thought they were going to be g of 3. They did not. So what I have to use is this understanding that the g of x function and the f of x function are inverses of each other. Kind of go back to your first understanding of inverses, right? When you find inverses of each other, the x's and y's, they switch. Okay, so like if in the f of x function, I have the ordered pair 6, 3, then the g of x function is the ordered pair 3, 6. All right, so that's what I use right here. So they're telling me that when I plug in 6 for x in the f of x function, I get 3. So that means since g of x is the inverse of it, when I plug in 3, I would get 6. So actually this is going to be g of 3, which is 6. All right, now I'm doing 1 over f prime of 6. F prime of 6 is negative 2. So the answer is negative 1/2. Okay, thank you for your patience there. 47. We have the function f of x, and it's telling us that g of x is the inverse. So again, we got this same thing here, but I think it's going to help us out because they gave us g of 3 this time. So a little bit simpler. So I'm going to do g prime of 3, I guess I'll start with just x, is 1 over f prime of g of x. So that's going to be 1 over f prime, because we're going to plug in 3 when you see x, f prime of g of 3. Now this time they gave us g of 3. All right, so we have f prime of g of 3, which is 1. Now watch this. They didn't actually give us f prime, right? But they did give us f of x, and I can find the derivative of f of x. The derivative of x cubed is 3x squared. Derivative of x squared is 2x. The derivative of x is 1. So if I plug in 1 here, I will get my denominator. All right, so 1 squared is 1. 1 times 3 is 3. So 3 plus 2 plus 1, which is equal to 1 over 6. All right, so I'm showing you different ways that they're going to ask you about the inverse function theorem, right? This one right here. 48. We're going to find the derivative of an inverse trigonometric function, all right? So I have the derivative of tangent to the negative first power of x plus the derivative, now watch how I write this one, of, let me move my constant multiple in front, the derivative of x to the 1/2 power. All right, so let's see what that is. I'm going to use my formula sheet for the inverse tangent function, which is 1 over 1 plus your argument squared. So 1 over 1 plus your argument squared. All right, and it does say that you would have to use the chain rule if we needed it, but we don't have it. All right, so we just leave it as 1 plus x squared in the bottom, plus 2 times, I'm going to put that together now, Move the 1/2 in front. Half of 2 is 1, and that's x to the negative 1/2 power. So the answer is going to be 1 over 1 plus x squared plus 1 over the square root of x, which is letter E. Okay, 49. This says arc tangent, but if you needed to rewrite it, you could. Right? Arc tan is just tangent to the negative first power of the cosine of x. All right, so when I find the derivative here, I am going to have the chain rule. So the derivative of the inverse tangent function of cosine of x, so that's 1 over 1 plus the cosine of x squared. And then remember, times, got to use the chain rule, the derivative of the cosine of x, which is negative sine of x. So I have negative sine of x over 1 plus cosine squared x, all right, which is going to be letter A. Number 50. All right, so which of the following does not require the use of the chain rule to find dy dx? All right, well, in part A, very similar to what we just did, you'll have to use the inverse sine derivative formula, which is 1 over the square root of 1 plus x squared. But then you'll also have to use the chain rule of the inside here. Right, you'll have to use the chain rule here. So it's not going to be that one. For the part B, right, for part B, you're going to have to use the chain rule because we have implicit differentiation. So when you have implicit differentiation, you'll have to use the chain rule to do the derivative of dy dx. So both of these will involve the chain rule. And then part D, you'll have the chain rule because the argument of your cosine function is x plus y. So the only one that does not require the chain rule is actually letter C. Okay, so we have if x squared plus y squared equals 25, what is the value of d squared y over dx squared at the point 43? If you were paying attention literally today when I was going over class, I know you're not going to watch this actually today, but we literally did the second derivative of this circle. So you can tell the textbook we use is just banking on the fact that you're going to have a question about a circle. So you would have to find the second derivative of x squared plus y squared equals 25. So I'm going to do this. I'm going to show you all the work, but we actually did this in class today. So we have the derivative of x squared plus the derivative of y squared equals the derivative of 25. So that's 2x plus 2y times dy dx equals 0. Move the 2x over, get negative 2x, divide both sides, and you get dy dx is going to be negative x over y. We already did that. All right, now I'm going to find the second derivative of this. All right, so I'm going to find the, move that negative in front to be, let me do it down here. So the second derivative, let me go over here since I'm going to need more room. So the second derivative is going to be d squared y over dx squared equals negative 1 times the derivative of x over y. So that's going to be, using the quotient rule, the derivative of the numerator is 1 times the original denominator minus the derivative of the denominator times the original numerator over denominator squared. So I'm going to replace, like we did in class, I'm going to replace this dy dx with what I already found it to be. So I can have just x and y, so I can plug in my 0.43. So negative 1 times y, and that's going to be plus x squared over y, all over y squared. I'm going to distribute that negative now, so negative y minus x squared over y squared. Get a common denominator in the numerator. So I get negative y squared minus x squared over y times 1 over y squared, which is equal to negative y squared minus x squared over y cubed. Okay, now we're not done. We need to plug in 4, 3. So x is 4, y is 3. So the opposite of 3 squared minus 4 squared all over 3 cubed. So that's going to be negative 9 minus 16 over 27, which is negative 25 over 27. So the answer is A. Okay, 52. All right, we're finding the second derivative of e to the x cubed power. Let's find the first derivative. So we have d dx of e to the x cubed. Remember, the formula says to write down e to the x cubed, but then times the derivative of whatever's in your power, which is going to be 3x squared. Now that's the first derivative. We need to find the second derivative here, which is going to involve the product rule. So the derivative of e to the x cubed is going to be e to the x cubed times 3x squared times the second one, which is still 3x squared, plus the derivative of 3x squared, which is 6x, times e to the x cubed power. All right, so that's going to be e to the x cubed power times 9x to the fourth power plus 6x times e to the x cubed power. If you factor out e to the x cubed, you'll get 9x to the fourth power plus 6x, which is going to be letter D. All right, that's 52. 53, another higher order derivative. All right, we've got the third derivative, so we need to do the first derivative, the second derivative, and then the third one. So here we go. Here's the first derivative. The derivative of cosine is negative sine of x, then minus, remember how to do the derivative of the natural log function down here, which is 1 over your argument times the derivative of the argument. So minus 1 over 2x times the derivative of 2x, which is 2. So this is, so 2 over 2x is just going to be minus 1 over x. So that is the first derivative. So first derivative. Let's do the derivative of this. The derivative of sine is going to be cosine. So that's negative cosine of x. And then if I do a little work here, right, if I rewrite this as, before I do the derivative, let me rewrite it as minus x to the negative first power. Okay, now here's the derivative. So we said that was negative cosine of x. Negative 1 times the negative is positive 1x to the negative second power. All right, so that's the, we rewrite it, and that'll be the second derivative. So plus 1 over, you know what, no, I don't want to rewrite it yet until I get to my answer. So let's find the third derivative. Derivative of cosine is negative sine, but we have a negative already, so that's going to be sine of x, and then minus 2x to the negative third power. So now to write it as how they wanted the answer, so minus 2 over x cubed. So that's going to be A. Okay, let's find the third derivative. Oh, wait, hold on. Was that the fourth derivative? Okay, that was the third one. Whew, that was the fourth derivative. That's the third derivative. Yep, first one, the second one, and I found it. There's the third one. Okay, now here's another problem where we find the third derivative, but we have to evaluate it at 2. So we have the first derivative is going to be 4x cubed minus 6x squared plus 3. So this is the first derivative. The second derivative is going to be 12x squared minus 12x, all right, to the first power, and then 3 goes away, so that's the second derivative. Here's the third derivative, 24x minus 12, so that's the third derivative, and we're plugging in 2. So 24 times 2 minus 12, that's going to be 48 minus 12, which is 36. Did something wrong, clearly. What did I do wrong? Let me pause it and let me figure out my mistake. Okay, I figured it out. It already gave us the derivative, the first derivative, so that's on me. So this is actually the second derivative, and this one is actually the third derivative. So none of that is needed. So actually I'm going to plug it into my 12 times 2 squared minus 12 times 2 So that's going to be 12 times 4, which is 48, minus 12 times 2, which is 24, which gives you 24. My bad. Just got excited. 54 is B. 55, almost there. We have a function f of x, and we want to find the instantaneous rate of change of f at x equals 3. So this is saying to find the instantaneous rate of change. I wonder if I put this in the form machine. I don't think I did, but maybe I did. But anyway, the instantaneous rate of change. Oh, I did. Instantaneous velocity. You could use that formula if you wanted to. But essentially, this is just asking you to find the derivative and plugging in x equals 3, right? The instantaneous rate of change is to find the derivative of this function, which is 3x squared minus 12x plus 8, and then evaluate it at 3. So that's going to be 9 times 3 is 27, minus 36, plus 8. That's going to be negative 9, plus 8, which is negative 1. 56. All right, this one, I had this on the test originally, but you're just going to use the formula sheet to find the derivative of cotangent. And the derivative of cotangent is negative cosecant squared x. So 56 is B. 57. All right, we have the limit as h approaches 0 of all this stuff. And if I try to plug in 0 right now, this is from one of the first lessons where before we did the derivative rules, that this is how you found the derivative. It's right here in your formula sheet, or we don't really use that much anymore. But the way we did was we're going to distribute, expand. So x squared plus 2xh plus h squared plus 4x plus 4h minus x squared minus 4x all over h. I'm going to cross out the stuff that makes 0. So x squared, cross them out. So we have x squared minus x squared is gone. 4x minus 4x is gone. So you're left with 2xh plus h squared plus 4h all over h. Factor out the h. So you have h times 2x plus h plus 4 all over h. And so the limit as h approaches 0 is going of 2x plus h plus 4. You're going to plug in 0 for h. It's 2x plus 0 plus 4, which is 2x plus 4. So this is essentially finding the derivative of a quadratic. So the answer is C. 58. So close. 3 more to go. We want to find the equation of the line that's tangent to the graph, which I think we already did this in part 2. Let me confirm. I definitely did that one in part 2. Almost there. Yep, right here, number 36. So 36, 2x plus 3 over 3x minus 2. Let me make sure it's the same. 2x plus 3 over 3x minus 2. And it is the same. So if you need to do this one, I believe it was, what I say it was 36. And it's B, so you can always watch part 2 again for number 58. Okay, 59. The derivative of x plus 1 over x squared plus 1. So this is going to use, I'm going to use the quotient rule here, which is the derivative of the numerator, which is just 1, times the original denominator, minus the derivative of the denominator, which is 2x, times the original numerator, all over the denominator squared. It's going to be x squared plus 1 minus 2x squared minus 2x all over x squared plus 1 squared. Combine like terms, you get negative x squared minus 2x plus 1 over x squared plus 1 squared. So we have our answer is, looks like it's going to be C. All right, so that's 59. One more, guys. We made it, the very last one. We're almost there. Which of the following does not require the use of the chain rule? So again, kind of similar to a problem we just did, right? Whenever you have this inverse tangent function, this argument, we're going to have to use the chain rule to find the derivative of that argument. We're also going to have to use the chain rule for this implicit differentiation, and we'll have to use the chain rule for the derivative of this trig function. So the only one where you won't need to use the chain rule is C. All right, guys, we did it. That's all of them. Hopefully, you'll have a chance to go over all of these and make sure that you are as prepared as possible for the test. Good luck.